Hello everyone, welcome back to another BGCSE past paper review. Today we're going to review a physics paper. It is a paper one from the year 2021. Again, as always, please remember to write your school number, your candidate number, your surname, and your initials before you start this examination. Also, you need to read through the instructions carefully, and if you have any queries or any doubt, please clarify those with your examiner. Let's go to question number one real quick. For question number one, it said, what is the definition of pressure? And quickly just to remind you about the formula for pressure is that pressure is equal to force over area. All right. And if it's equal to force over area, therefore means the definition is actually force acting per unit area. And so already option A is our correct answer. All right. So it's not volume, which is stated in B or D, and it's not mass, but it's actually force acting per area. Let's look at question number two. In question number two, it says, which of the following machines is an example of a second order or second class lever? And so L is the load and E is the effort. And so quickly, let me remind you again about something that you need to remember to classify levers, whether it be first or second class, and it is FLE. And FLE, it is based upon what is in the middle. And so in the same order, if the fulcrum is in the middle, then it is a first class lever. If the load is in the middle, then it is a second class lever. And if the effort is in the middle, then it is a third class lever. And so looking through the answers, looking at option A, the pivot here is at one end, the effort is at one end, and the weight or the load is in the middle of the wheelbarrow. So already this is a second class lever. Looking at B, the load is at one end, the pivot is in the middle, and the effort is at the other end. So therefore, it's a first class lever here as well. For the arm, pulling up something, then the ball or whatever circular object is in the hand, it is the load. The pivot is at the elbow, and the bicep will be your effort. So therefore, it's a first class lever. A pair of scissors, the effort is in the handle of a scissors, the load is what you're trying to cut, and the pivot is in the middle. So therefore, this is a first class lever as well. All right, so let's go into question number three. And question number three, it said the picture shows a dune buggy. It said why is it equipped with wide tires so it can go on soft surfaces? And so of course you don't want to damage a soft surface. So there's a number of things that could happen here. And one, if you go through option A, it's a decrease in pressure, and which seems like the correct answer because firstly, you need to know that a greater area of contact give you a lower pressure. And so based on the formula as well, think about it in this way. So if you think about the formula P, which is pressure, is equal to force over area. And I want you to remember that weight is the same thing as area, right? So if it's the same weight, but you have a bigger area of contact, then the pressure will be less, okay? So greater area, less pressure. Again, remember that area and pressure, they are inversely related, right? However, force and pressure are proportional to each other, all right? And so, again, it is to decrease the pressure onto it. So increase friction, no. To increase the pressure, no, actually decrease as I mentioned. So increase the weight. No, the weight will be the same. The only thing that the wheel might do is to spread the weight across a larger area. So decrease the weight in one spot. And so if they have decreasing weight right here, then we could have considered that in terms of decreasing the weight on one spot, but not to decrease the weight of the car, but decrease the weight of the car acting only on one spot. So wider area, wider surface area, the force will be spread out. All right, let's go to question number four. In question number four, the diagram shows a balanced uniform horizontal bar, and it said, what is the mass of object M? And so what we're going to use here is a principle of moment. And the principle of moment states that the total anti-clockwise moment is equal to total clockwise moment. And so if we look at this bar carefully, we know that the 200 grams is causing a anti-clockwise moment, while the M mass will cause a clockwise moment. But what is important also is to note that the 200 grams, again, normally when you're doing moment of force, you actually will change the mass into force. All right, but you do not need to do that because the answer will be the same anyhow. And a matter of fact, our answer going to be in grams, so you can just leave it in grams. There's no issues in changing it right here. There's no need for that. So the first thing here, as I've said, at the moment is there's a weight or the mass or the force acting from the pivot. And so for the anti-clockwise moment, it's going to be 200 grams multiplied by 50 centimeters acting from a pivot equals to our mass, which is m that we do not know at this time, but it is multiplied by 20 centimeters acting away from the pivot. So here now, 20 multiplied by 50, what you get there is 10,000. So going to be 10,000 equals to m20, okay? And so to make m be the subject of a formula, m equals to 10,000, all right, divided by 20. And so that gives us 5,000 grams. All right, so therefore A, no, yeah, that's say 500. So yeah, that's 500 grams, not 5,000, but that's 500 grams. So let's just change that. That's 500, not 5,000. So D is our correct answer in this case. So the mass is 500 grams. All right. So D is the correct answer. All right. So awesome. All right. And just to go to our next question now, which is question number 5. And question number 5 here, it said that a man has a weight of 500 Newton. He climbs 40 steps, and each step is 0.25 meters high. It said, what is his gain in gravitational potential energy? And so just to make a quick note right here, in terms of gravitational potential energy, in terms of formula, let's say potential energy, which is PE, is equals to mgh. All right, so the gravitational potential energy is equal to mass times gravity times height. But let me quickly just clarify something quickly, or show you something here. We want to know what is mg. We do not have mass inside of this statement, but I'm going to show you something really quick. All right, so the first thing we can find our total height. So let's talk about total height first. And so our total height here equals to 40 steps, and each step is 0.25. So we're going to say 0.25 multiplied by 40. And so that is a quarter of 40, and that's going to be 10 meters. All right, next now, let's look at our weight, or mgh. So mgh, just to make sure you know this, so mgh is equal to weight, and so weight is a force. So therefore, weight here is 500 Newton, with the same thing as mgh. So what we can now say is that the potential energy here is equal to mgh, which is the same thing as weight. So it's going to be 500 multiplied by here, which is our total height. I said 10, yeah? So 10 meters is our total height. So it's going to be 5,000 joules of energy. All right, so there we go. So option A here will be our correct answer. All right, so now we are good to go to question number 6. So question number 6, let's scroll down a little bit to that. So question number 6, which graph correctly shows how the volume of a fixed mass of gas at constant temperature varies with pressure? And so for this one here, when you see constant temperature, you know that you're talking about Boyle's law. And so in Boyle's law, it states that volume is inversely related to pressure. So the higher the pressure is, the smaller the volume will be. So in think about gases, if you squeeze them together by increasing pressure, the volume will decrease. And so if you look at option A, this cannot be a correct answer, because saying that volume and pressure, they are proportional to each other. But in B, which is a good graph, we say that basically this is a inversely related graph. So as pressure decrease, then the volume will increase. All right. For C is incorrect because it shows up a proportional level first and then it tapered off. And then in D, it is saying that pressure does not affect volume at all. All right. So B is definitely the answer for that question. Question number 7. And in question number 7, let's go back a little bit up. Question number 7 said, which velocity time graph best shows the relationship between velocity and time for a parachute jumping, for a parachutist jumping from an aircraft before the parachute opens? All right, so what you need to know here now, that the person is falling, right? So if the person is falling, then the person must be accelerating due to gravity. So there's an acceleration, which means that there's an increase in velocity over time. And so we're looking for a graph that's showing an increase in velocity over time due to acceleration, and therefore going to accelerate due to gravity, as I mentioned. And so if you look at graph A, it is showing an acceleration here, all right, and it is under the influence of gravity, just to mention that. All right, so graph B showing you, yes, is accelerating, then it's going to come to a constant speed. Absolutely not. It's going to keep falling all the way until it hit that ground, right? So it is option A. All right. Let's look at question number 8. It's a steel sphere falls from the upstairs window of a house. What can be said about the acceleration of the sphere if air resistance can be ignored? And say, let's go through this now. If you think about air resistance as being nothing, then think about the ball falling. And so the ball is right here, just to kind of highlight it. So it's falling. So what can we say about it? Depends on the density of the sphere, not necessarily true. It depends on the mass of the sphere, not necessarily true. But of course, if you have bigger mass, then you're going to create a bigger force. And want to talk, we could talk about why. But there's an increase. It said it increases as the sphere falls, and it said remain constant at as the sphere falls. All right. So what we're looking for here is acceleration, and so acceleration of the sphere. All right. So the acceleration is the same because it again it's under the influence of gravity, as we talked about the first question before. All right. So the acceleration only depends upon gravity in this case, and again is on the influence of gravity. So D is the correct answer. The gravitational pull, the gravitational acceleration will be the same throughout the entire journey. Now, for question number 9 here says, what distance versus time graph shows an object moving at uniform speed? And again, this is distance over time. So if you look at what they're saying as time increase, the distance will increase, which is somewhat true, but over a period of time, it will not be the same because again, here we say it must be uniform speed. For B, what is happening B is that here the distance is not changing, and no matter what the time is, and so therefore this object is actually not moving, it's stationary, it's at rest. And for C, there is an increase, definitely, but this is a square value here, so this is not necessarily the correct answer. And in option D, here, for option D, what option D is stating here is that as time increases, then there is an increase in distance as well. So they're increasing directly proportional. So this would be a constant speed for sure. All right, so let's look at the next question now, and which is question number 10. And we're winding down. We're going to go through as fast as we possibly can. And for question number 10, is the graph shows a cooling curve for a solidification of liquid paraffin wax. So this is a cooling curve for, I know this, matter of fact, let me make sure to point this up because this is saying this is liquid. So this is liquid paraffin wax. All right, so the fact that it's starting as a liquid, that's very important. So you need to know what is the physical state of the substance whenever you're talking about cooling curve or heating curve. You need to know that. That's very important. So here you're asking now, which letter on the graph shows a point where there was a mixture of liquid and solid. And so liquid and solid is when the temperature is actually the same. I'm going to talk about that as I go through the different points. The temperature must be the same. That means there is pretty much where it is actually freezing. So firstly, the substance here, as they mentioned here, it starts as a liquid. So we know that from A, it is a liquid. So this is a liquid at A. And going through the entire line right here, it must be liquid just the same. So right through, it is a liquid. All right, so what I want to make a point here now is that once there is a change in temperature, the state remains the same. Okay, the state will remain the same. So the liquid is cooling, and the liquid cools all the way to this temperature. So at point B, that will be the lowest temperature that the liquid can go. Okay, that's the lowest temperature liquid can go. So guess what? At point B, it is pretty much liquid at its lowest temperature. Now moving from B, it is still liquid, but it's going to solid. So from here now, between B and C, it is liquid changing to solid. All right, just a mention right there. But at B, it is only liquid. Okay, at B, it is only liquid. However, at this point, I'm going to point out something right here. At this point, it's moving here when it turns purely solid. So right here is just at the point right here when you're going to change the graph, it is pure solid, which means solid only. Let me say solid only rather than saying pure solid. So it is solid only at this point. At the peak is solid only. B is liquid only. All right. And so here now it's changing from solid to from liquid to solid. And so at some point along here, you will have partly liquid, part solid. And so C has to be the correct answer. D again is also solid, but it's going to be solid at this lowest temperature, right? So that's also solid there. Remember, once there's no change in temperature, once there's no change in temperature, there is a change in state. So you need to remember that. Change in temperature, no change in state. All right? A change and no change in temperature, there is a change in state. You need to remember that. So coming from A to B, there is a change in temperature, therefore the state is the same. Moving from B all the way to C to this point right here, there is no change in temperature, which means there will be a change in state. And going from this graph sloping down to D, there is no change in state. You need to remember that all substances actually change. So yeah, C is the correct answer here. All right, so let's go to question number 11 now. And the question number 11 is a soccer ball moving with a velocity of 25 meters per second has a momentum of 12.5 kilograms meters per second. Here said, what is the mass? What is its mass? And so this is based upon momentum. And so let's quickly just remind the formula for momentum. So momentum is given as this, mass multiplied by velocity. And so therefore we know for sure now, if you want to find mass, it's going to be, so mass will equals to the momentum divided by the velocity. All right, and so by virtue of this, what we're going to get here is that our mass will equal to the momentum. So the mass, let's say m, is equal to the momentum, which is 12.5. So it's going to be 12.5 divided by 25, okay? So if you have 12.5 divided by 25, what we're going to get here is 0.5. And so that's 0.5 kg, okay? And so A is our correct answer. Let's go into question number 12. And the question number 12 is say a force of 100 newtons is applied to the handle of a nutcracker. The nutcracker exerts a force of 650 newtons on the nut. What is the mechanical advantage of the nutcracker? And so mechanical advantage, just remember the formula for mechanical advantage is, so MA equals to the output force over the input force. So output force, so you can say output force over input force, okay? Over input force. And so that now will equal to here, output. And so the output force, as we notice here, will be equal to the 650 Newton. So going to be 650 divided by 100. And so 650 divided by 100, what you're going to get there is 6.5. Okay? So 6.5 is our correct answer for this answer, question number 12. Question number 13 is which of the following is an example of a scalar quantity? Is an example of a scalar. Acceleration is vector, momentum is vector, speed is a scalar, velocity is also vector quantity as well. All right, because they will have both magnitude and direction. Scalar only has a magnitude, which means it only has a size. Question number 14 is an object will stay at rest or in constant motion unless acted upon by an external force. This statement represents which law of physics? And this law here is Newton's first law of motion. All right, so object will continue moving, stay at rest if it's at rest, all right, or otherwise if it acts upon an external force. The only way it could change, there must be a force acted on it. All right, so question number 15 is which property best describe the image formed in a convex mirror? And a convex mirror here will form what a smaller image. Just to mention that, so the image must be diminished, and the image will also be a virtual image as well, and it will be upright. So therefore, B will be our correct answer. And so if you notice, like say for example, in the food store, like in the supermarkets, you will see at the ends sometimes you will see convex mirrors, and you can see the entire store. So, but it's small in size compared to the store itself, and it's always upright and it's virtual because it's formed behind the mirror itself. All right. So definitely that. Sometimes you see it on on some corners of roads as well, so you can see around the corners. All right. Number 16. It's a gasoline storage tank at the Bahamas Oil Refining Company are painted silver. What does this reduce? And so if it's painted silver, that means it's shiny. That means it's going to reflect some light. And so therefore, if it's reflecting light, that means less light or radiation will be absorbed. So you're going to decrease radiation. All right, so it's decrease the absorption of energy by radiation, right? Because, and again, the reason behind that, remember, if radiation enters the tank or a tank get too hot, then an increase in temperature will cause an increase in volume. And if there's an increase in volume, you'll also have an increase in pressure. And so if the pressure of the tank gets too high, it can cause an explosion. Right? So it's silvery to reduce that. All right, for question number 17, it says which of these waves has the longest wavelength? And so let me just remind you about a little nice good thing that what we have done in the previous review. And so we give you the electromagnetic waves as being R, M, I, MIU, V, V, X, and then G. And remember what you use to remember this is radio my information. All right, so radio my information verbally. Let's change the V. I make a mistake. The V to you. So radio my information verbally unless X news is gibberish. So we use that to remember the order in which these electromagnetic waves are organized. So again, radio my information verbally unless X news is gibberish. And so going from radio waves to the gamma radiation, what happened there in terms of wavelength is that wavelength will decrease going that way. So the longest wavelength there must be the radio, okay? And also going, let me just quickly, I'm going to show you on this so quickly. Again, I'm going to remind you because I think most of you would have seen that already. Going this way, we have a decrease in the wavelength. So wavelength here will decrease, but however, going to this way, the frequency will increase to maintain the same speed. Okay, because remember they move the speed of light, right? In a vacuum that is. All right, so just that you need to know right there. And again, remember that we talk about the X-ray and gamma ray being those are ionizing electromagnetic waves, and from ultraviolet into radio waves, those are the non-ionizing waves, right? Just to mention that there. Number 18, for number 18, it said, when must the total momentum of a flock of identical birds be zero? When the momentum should be zero. And it said, if they come to rest, and of course, anything at rest must have a total momentum of zero because it's not moving, because momentum is actually the mass times velocity. All right. And so therefore, A seems the correct answer right there. It's if they're flying in different directions, no. If they're flying the same direction, no. If they take off from the ground, no. Once there's no velocity, there's no momentum. All right, just to make a note of that. Number 19, it said the speed time graph diagram below shows the motion of a small truck, during which segment is acceleration equals to zero. And we're looking for acceleration equals to zero because what acceleration is a change of velocity over time. And so if velocity is not changing, if velocity is the same, that means the object is not accelerating. And so the only point right here is from F to G. It is moving at a constant speed. That means there is no acceleration at all. For the first line right here from E to F, it is accelerating. From G to H is accelerating. From H all the way back down here, it is actually decelerating, which is a negative acceleration. So it's still accelerating, but in a negative value. All right, so the answer there must be FG. So therefore, B is our correct answer for number 19. All right, let's go to question number 20. All right, and in question number 20, let's just quickly scroll on to that. There, okay. So the graph below shows how the count rate of a certain radioactive isotope changes with time as it decays. And say, let's see what they're asking us here now. So we have a count rate on the y-axis. and we have the days or time on the x-axis. So what is half-life of the radioactive isotope? All right, so to find half-life is the time taken for half the substance to decay, and we start at 80. So what we're going to look at is 40. So 40 is the half the amount from 80. So we start at 80. Here is the starting point, and so half of 80 is 40, and so the time that it takes to come to 40 is actually 2 days. Okay, so 2 days will be our half life. And just to make a mention right here again to continue with this, half of 40 is 20, right? And so 20 go to 4. And so if you notice again, it takes another 2 days for half of it to break down. If you go to 10, which is another half, you should go to another 2 days again, which is 6. So you can do half-life like that. And then the other half-life would be to 5, and then so on and so on and so forth. All right, so let's go into our answer. Our answer is 2 days. Half-life is 2 days. Question number 21 is, which device converts electrical energy into kinetic energy? And so what you're looking for here, again, electrical energy, convert electrical energy into kinetic energy. And so a battery is actually chemical to electrical. A generator is actually kinetic to electrical, so it's opposite on what you're actually asking. Motor now, it uses electrical energy to cause turning, so the motor is a correct answer. A transformer, no, is a spare electrical energy that is flowing through it. All right. All right. Question number 22. It said, which component is shown in the diagram? And if you remember from a previous review, the one before this, we know that it is a thermistor. All right. So the thermistor, this is it right here. And a thermistor, remember what it is? It's a simple device that changes its resistance with a slight change in temperature. All right, just remember to remind about that. Now, question number 23 is said a permanent magnet is made by stroking which type of material with an existing magnet. And so here now we're going to have here is a soft iron. All right. A soft iron, no, soft iron cannot be, because soft iron will form temporary magnets, I should say. We're looking here for which can form a permanent magnet. Okay, so a permanent magnet is not soft iron. Soft iron form temporary magnets, or what they call electromagnets. Copper and aluminum will not form magnets at all. So permanent magnet is by hard steel. All right, so temporary magnets or electromagnets is by soft iron. So yeah, D will have to be your answer there. All right, question number 24. In question number 24, it said, which change will not increase the strength of the magnetic field in the coil of a simple electric motor? So what will not cause an increase in that strength of magnets? So here is adding soft iron core. Definitely that will help to build it up because of what it actually needs. All right, but let's go to the other options and see here. It's an increase in the current. Yeah, increase in current give you an increase in magnetic field as well. Increase number of turns definitely will increase the magnetic field. It's an increase the resistance of the current, providing the voltage remain constant. And so if you increase the resistance with the same voltage, what's going to happen is you're going to have less current flowing. And so a decrease in current is a reduction in the magnetic strength. So D has to be the correct answer there. All right, so question number 25. It's an atom consists of 3 subatomic particles. Which of the following exist in the nucleus? So in the nucleus of an atom, we have protons and neutrons. So looking through this, D is the correct answer, protons and neutrons. And protons and neutrons equal to the total mass of the atom, right? Electrons are found on the shells or on the orbitals surrounding the nucleus, all right? And again, protons is positively charged, neutrons is zero charge. Protons and neutrons, they have mass. Electrons do not have mass, and electrons are negatively charged. Question number 26. It's a uranium-238 has an atomic number of 92. It decays by alpha decay to become thorium. What is the mass number and atomic number of thorium respectively? So what we're going to do here is looking for mass and the atomic number. So first thing you need to know in terms of this decay is that if you decay by alpha, just to make a quick thing right here. So you're going to decay by alpha. What you need to remember, you're going to decay, the mass number decreases by 4, and the atomic number or proton number decreases by 2. All right, so starting with uranium, and so if I give it the mass number as 238, that's the mass number that is given, and the proton number or the atomic number, same thing, proton and atomic number, they're the same thing, and so this is 92, and so if this decreases by 4, then what we're going to have is 2 34. And then the 92 will decrease by 2. So what we're going to get here is 90. So the answer that we're looking for here is 2, 34, and 90. All right. So our answer there is 2, 34, and 90, which is B. So B is our correct answer. All right. So let's look at the next question, which is question number 27. And it said all radioactive sources of a half-life. Which statement about the half-life of a source is correct? All right, so let's go through it. So for option A, its half-life is a time for the reactive source to become safe. That is not true at all. It said if for B, it said its half-life is a time take for an atom to decay. Not true. It's not just the atom to decay. There's something specific it must state. It's half of this substance. So in option C, it said it is half the time, which is not true. Okay, so half the time is not true. It's half of the substance. So it's half the time it takes for the count rate on the detector to need the source to be 0, which is not true. For option D, it is a time takes for the count rate on the detector near the source to decay by half. Right, and so this is indicating that half the substance is decaying. So the time taken for half of that substance to decay. So D has to be that correct answer. Now, question number 28, it now says strontium-90 is a beta emitter. I mean, it emits beta. Which is best describe a beta particle. So beta particles, when we talk about beta particles, the first thing to remember about beta particles is that they are fast-moving electrons, okay? They are fast-moving electrons. Alpha resembles an helium, okay? Alpha resembles helium. That's as we talk about up front, or the question before this, is that we have mass number 4 and proton number is 2, which is resembling the helium nucleus. All right, so question number 29. Here now, question number 29. It said, which of the following is a function of insulating materials? So if you insulate materials, what it does is actually to prevent current from flowing through it. So insulator prevents current from flowing through it. And so it's a conduct very large current, which is not true at all. B saying preventing an open circuit between the voltage source and the load is preventing an open circuit, which is not true at all. If you put an insulator between something, you're going to stop the current from flow. So actually, it will cause an open circuit. So like say between a switch, you put a piece of paper between a switch that they cannot close or current cannot flow through the wires, then yeah, that will actually create an open circuit. All right, it said now preventing a short circuit between conducting wires. All right, and so let's for you to understand this. I'm going to draw something for you quickly. So if you think about wires in this way, right? So this is a wire right here. So we're going to have two different wires. And then inside you have a copper wire, for example. So inside of this wire, you have a copper wire here. And then you have a next wire beside this one as well. All right, and so inside you have the wires. And so just to kind of point this out. So the wires could come beside each other to prevent. Let me put highlight right here. So the highlight is the wire inside of the insulator, right? So let's put it here. So the wire in the middle, the yellow is the wire. I should put yellow on the outside, but that's fine. So the wire is in the middle. The red lines represent the casing of the wire or the rubber part of the wire. So if you have two rubber parts touching together, the wire is not connecting together, so it's going to prevent that short circuit from happening, right? So that's why you notice like speaker wires, for example, electrical wires, they have rubbers around them. And so even if you touch the wires by the rubbers, they will not create a short circuit. But if you strip the wires now, or strip the plastic or the rubber from the wire and put them together, then you create a short circuit and it could be dangerous. All right, so question number 30. In question number 30, it said, what is component H? And component H, if you notice how the line go through it, and so it is a variable resistor. All right, component H is a variable resistor. A is an ammeter, and V is a voltmeter. So yes, this is a variable resistor right here. All right, so number 31. It's a diagram shows a swinging pendulum. So this is a swinging pendulum. We have a start right here, and the bob is a round thing that's moving. So this is start, and it goes up from 0 point to 1, 2, 3, 4. It's at which point is the kinetic energy of the bob is at maximum. Kinetic energy is maximum. So just to kind of quickly point out right here, at the start right here, the highest point or the maximum height, this is pretty much potential energy. Let's say PE, right? So that's potential energy right there. About halfway, because this is the midpoint, this is at the rest point right here. About halfway, you have potential energy equals to kinetic energy. So right here we have potential energy equals to the kinetic energy. All right, that means half the potential energy will convert to kinetic energy at the midpoint. If it is exactly midpoint, potential energy equals to kinetic energy. All right, between here now, the numbers may vary, okay? But of course, potential energy at this point will be higher than kinetic energy. At this point, they'll be equal. At point 2, you will only have kinetic energy because the potential energy totally converts into kinetic energy. So at point 2, at the rest position right here in the middle, then that is a point when there's no height of the bob, and there's no height, all the potential energy is now converted to kinetic energy. And going up to 3 to 4, there's a decrease in kinetic energy and there's an increase in potential energy. So again, at point 3, kinetic energy that was gained at point 2 is now equal to potential energy, exactly halfway through. At point 4, there's no kinetic energy anymore. It turns into potential energy. And coming back, the opposite thing is happening. All right? All right, just to make a mention of that. So again, at what point the bob, at which point is the kinetic energy of the bob is at the maximum, and that's going to be at point 2. Okay, so point 2 is the maximum kinetic energy. All kinetic energy, a matter of fact. Total kinetic energy, no potential energy at all. All right, let's go to question number 32. Question number 32, it said at a track and field meet, a pole vaulter runs along a flexible pole, runs with, matter of fact, a long flexible pole and uses it as an aid to lunge up into the air in order to jump over the high bar. So if you look at the diagram carefully, as you go on now and then start to launch over the bar, there is a vault that actually helps him to do that. And it said, what is the main energy transformation occurring at the athletes as the athletes run, bends the pole and reaches the highest point above the bar? So as he's running, you know that he's going to have a kinetic energy, right? So we're going to just put them in quickly. So here he's going to have a kinetic energy, KE, kinetic energy. Right here he has the maximum potential energy. But when we talk about the midpoint right here, what is happening here is a conversion from kinetic energy to potential energy. But what is causing that? It is the pole, okay? So as he's launching towards the top, there's a conversion that's happening here. And so here, if you notice, is a stretching or a flexing of the pole. And so we can call this now elastic energy. Let's say elastic energy right there. All right. And it's also as a potential. So we can call it elastic potential energy at that point. All right. And so let's go in through and see which change is happening here from kinetic energy, elastic potential, and then the potential energy. And so we're going to look through the answers now. So kinetic energy first, which is either C or D. And then you're going to have elastic potential energy, which is now D. So D is our answer. And then we have gravitational potential energy, which is same as potential energy. So therefore, D is the correct answer right there. All right. So it's the pole that is actually bending, and that called that launch. And so therefore is the elastic potential energy in the middle. So 33, it said which row in the table now shows the symbols of equivalent units for the joule. So what is a joule equal to? All right, and so let's just quickly run through them real quick. And so in that in option A, watt second is a joule, Newton meter is a joule, kilogram meters per second square is not a joule. So that is wrong for this point. So this piece is the wrong point right here. For option B, kilogram meters per second square, that is a force. That's what force is equal to. All right. And so force, yeah, that is force right here. So this is force. Newton per meter is also a joule. So this one is wrong because this is force. This is not equal to force. Newton per meter is wrong as well. So that's not the correct answer right there. Watt per second is also wrong. So everything in B is wrong. All right, but watt second is also energy, right? Remember that we are watt power second, or power times time is energy. Kilowatt hour is correct. Newton meter is correct. Watt second is correct. And kilowatt hour is same thing as, like you're saying, is a lower version of watt second, right? And that's how we actually measure electricity. So watt, kilowatt into watt, hours in the second. So they are the same thing. So they are correct. What is wrong here is Newton per meters and watt per second. So correct answer here has to be C. All right, let's go to the next question now. And the next question, question number 34. So the graph represents the cooling graph of a substance. And it said, what is the freezing point of the substance and what is happening to the kinetic energy of the particles in the substance during VW and during XY? All right, so let's talk about, again, remember we talk about this in terms of change of temperature, there's no change of state. All right, and now again, when there's no change of temperature, there is a change of state. All right, so I want to look at what is happening at VW and also what is happening at XY. So let's quickly just make some notes right here quickly. So again, it's a cooling curve. So we're gonna start, since there's so many different changes, we can start this as a gas. So this is gonna be a gas right here. So between V and W, that is a gas. And just after, let me put it a little bit higher, but because this represents the entire line, so that's a gas. Between V and G is actually gas to liquid. So the gas is going to turn into liquid here. There's a change of state because there's no change of temperature. W to X, we're going to move now from the liquid into, so this is going to still be a liquid right here, and it's going to be liquid only. Okay, so here's liquid only. So after L, after W, sorry. So let's just go back again. So UV, that's as a gas. From U to V is a gas. From V to W, there's a gas to liquid. So at W, it's only liquid, and there's a change of temperature. So all the way to X is only liquid. And then between X and Y, there's no change of state. So right here, you can see the liquid is turning into a solid. Okay. And then now from Y to Z, it is still a solid. Okay, still a solid. All right, just to make a mention right there. All right, so let's look at now what is happening at between V and W. So V and W is right here. There's a change of state into gas to liquid. That's what we know for sure. All right, and also during X and Y, X and Y, as we mentioned here, there's a change between liquid and solid. All right, so let's go to the chart and see exactly what is going on right here. All right, and what we're looking for is in terms of, it's what is the freezing point? What is the freezing point of substance at X? And what is happening to the kinetic energy of the particles of the substance between V, W, and XY. So let's look at the freezing point first. And freezing point is when it actually changes into a solid, okay? So let's go to that real quick. So when does it become a solid? All right, so notice here is converting from a liquid to solid. So notice it's solid right here. So from Y is a solid. So right across right here is the solid form. So that is 100 degrees Celsius is the freezing point. All right, that's when it turns to solid or pure solid, fully solid. All right. And so it could go below 0. So the solid could be below 0, but it's still solid. But the freezing point is 100. All right, so we're going to look for 100 in this. And so it's between A and B. But let's talk about what is happening to the kinetic energy between V, W, and also X, Y. All right, so VW first. So VW, there is no change of temperature. And remember now that kinetic energy is proportional to temperature, right? So between VW, there's no change of temperature. That means the kinetic energy must be the same, all right? But as temperature now drops between X and Y, or X and Y again, there's no change of temperature. So again, is all constant. All right, so both VW, there's no change of temperature, and XY, there's no change of temperature. So therefore, in both cases, the kinetic energy remains the same. So look for 100, and both remain the same, and that B is our answer. Again, kinetic energy is proportional to what? Temperature. No change of temperature, the kinetic energy remain the same. 35, and we're getting there. So for question number 35, now it says diagram shows two identical beakers. Each contain the same mass of pure water. The temperature of the water in beaker P is 30 degrees Celsius, while the temperature of the water in beaker Q is 60 degrees Celsius. It's a 50-gram aluminum cube at 20 degrees Celsius is placed in each beaker, right? It said which substance gain the greatest amount of heat energy. So what is different between these beaker here? Notice again, um, the same amount of water, but the only difference is the temperature, right? And it's asking you which of them greatest gain the greatest kind amount of heat energy. And so if you think about it, if the same volume at higher temperature, then therefore you have more energy in that one, because again, a greater temperature equals to greater amount of energy. And so therefore the aluminum cube in beaker Q must be the one that gains the most energy because they have a higher temperature. The same amount of water, but at higher temperature. Therefore, it must be the one with the highest energy gain. 36. The diagram shows a simplified model of a solar heater, right? It's a which uses energy from the sun to heat water. Now we said, what is the reason for painting the panel in the solar collector black? And it is to do what? And so to paint anything black, the first concept you should come to your mind talk about radiation is the absorption, to absorb more heat. Okay? And so let's look at option A, so improve the rate of absorption of infrared radiation. Okay, that's the answer right there. Once you talk about more absorption, yes. But let's look at B, to improve the rate of emission. No, that's actually given off, but is not correct. So black absorb. All right, to reduce heat loss by convection. Well, it could reduce heat loss, but it's not by convection, because more heat absorbed is more heat will be conserved. But the word is convection is not true, because again, is not convection is inside of the liquid itself, so that's not going to affect convection at all. It's a reduced heat conducting properties, which is not true at all. So definitely A is our correct answer. Improvement in terms of absorbing radiation. 37. It's a metal ball is heated, right? And it's shown here as you see. So what quantity of the ball decrease? So if you increase temperature, or you apply heat to the ball ball will expand, right? And what will expand it is volume. So you get larger, take up more space. So density, let's hold on to density a little bit, because density is given as the mass over volume, right? Now, just to point out right here now, if density is equal to mass, let me say density is equal to mass over volume. The density equals to mass divided by volume. So if you have a greater volume, then you have a smaller density. And it's a which of these decrease. So again, the mass is the same of the ball, but as you eat the ball, the volume should increase. So you have an increased volume, and so greater volume give you a lower density. So density looks good, but it's got diameter. Diameter expand because it get larger, the ball will expand. So yes, it will increase. Diameter will increase. The mass will remain unchanged. The mass will remain unchanged. The same mass is there. The volume will increase. So the only thing that decrease actually for real is actually density, because a bigger volume, as D will suggest, that volume increases. For the same mass, because mass remain constant, the diameter also increase, so density will decrease. Bigger volume over the same mass, decrease in density. 38, you see a water wave approaches shallow water close to the beach. What happens to its frequency, speed, and wavelength of the water wave? And so just to mention this, coming from deep to shallow, the wave actually moves slower. So speed has to decrease, that's for sure. Okay? And so what happened here again is that you also have a shorter wavelength. So we're sure about two things, is that the speed will have to decrease and the wavelength will have to decrease. And so if you look through these two columns, you realize that the only answer here that has both decreasing is actually C. Now the frequency will be the same. Why the frequency remain the same? The frequency remain the same because simply put, the waves start at the same point, which means the same vibration or the same disturbance. So if I have the same disturbance, mean the same amount of waves produced per second. So therefore the frequency remains the same, but there's a decrease in speed and there's a decrease in the wavelength. All right, so let's go into this. So only thing that is constant there is frequency. 39, and we're getting close. So as a student takes a pinhole camera, right, and uses it to investigate the properties of light, you see a simplified model of the image formed in the pinhole camera is shown. So we have the image here in the pinhole camera. Let me just put a little highlight right there. So that's the image right there. So image is upside down, which is inverted. That's the object over here. Let's put O right there. All right. And they said now, he said, how does the image appear after the pinhole enlarge? To make the pinhole bigger, what will happen here? All right, the bigger pinhole, it means that you have more light going in, right? And so if you have more light going in, however, the image will not be sharp. It's going to kind of spread out and get a bit larger. So the image get a little bit larger, and so going to spread out, and so going to cause some level of blurriness into it. So you get up, it's going to be brighter but blur at the same time. So that's a really concept that you really have to think about. The brighter means that more light is getting into it because of a bigger hole, but the image itself is spread out. So remember now, if you spread out image, it started to become, if you want to use the word depixelated, which is, don't use the word depixelated at all, but it can be depixelated if you think about it in that sense. Wider image now, you're not going to see it as sharp. So you're not going to be in focus as much, or it won't be as sharp as how it should be. So therefore, it's going to be a little bit blurry, but you're going to see it bright. You're going to see bright colors. All right, 40. It's the plane mirror. The two plane mirrors are placed at right angles to each other, as shown in the diagram. It said the angles in the diagrams have not been drawn exactly as measured, and measurements should not be taken from the diagram. All right. So he said the angle now, which is R1, which is actually the angle of reflection, 1 is 50 degrees. So we know that R1 is 50 degrees. And they said a ray of light reflects on mirror 1 and reflects from this mirror into mirror 2 and is once more reflected. So notice there's a reflection come here, reflection come here, reflection come here. And now it asks us now, what is the size of the angle R2, which is the angle of reflection in the second mirror. All right, so let's now look what is happening here. So first and foremost, I must point out where the mirrors are. So mirror 1 here, mirror 2 here. It actually labels, so that is also fine. That's the back of the mirror. All right, so we don't necessarily need that. So let us quickly talk about something here now, something different. All right, so what we need to know here in terms of working this out is if we know for sure. All right, let us go the longer road. So here you're going to be 50. We know that R1 is 50 based on the statement that is made right here. And also we know that angle of incident also equal angle of reflection as well. Between R1 and the mirror itself right here, it's supposed to be 90 degrees. So therefore here going to be 40. Okay, that is 40 degrees right there. Okay. And then in a triangle adds up to 180. So if a triangle adds up to 180, and here we have 40 plus 90, it is 130. And so 130 from 180 gives us 50. So right here going to be 50, right? And if right there is 50, we know that between the normal and this angle is supposed to be 90. So right here going to be 40. So that's how we kind of work it out to kind of map it and see that means. And if right there is 40, then R2 must be 50, okay? Sorry, must be 40 as well, because the angle of incidence must equal the angle of reflection. So if the angle of incidence on the second mirror is 40, then the angle of reflection must also be 40. And so behind right here going to be 50. That they did not ask us for that. But R2, what is R2? Let's go quickly. I'm looking for 40 based up on this. And so A is the correct answer right there, 40 degrees. All right, question number 41. Now we're getting really close in sight to the end. And it said, which ray shows the possible path for a ray of light leaving glass and entering air at an angle of incidence less than the critical angle? And this is a very important thing for us to know right here. So if it's less than the critical angle, all you're going to have is you're going to have an refraction taking place. And what's going to happen here also we're going to refract, increase in greater angle of refraction, because once it's less than it, then yes, you're getting closer to the critical angle, then the angle of refraction also will decrease, right? So just to mention that, and so eventually you're going to have what they call total internal reflection. So here is B is a better suited diagram. All right, so therefore it is an increase in angle of refraction right here, based on what is happening. If it's below the critical angle, going closer to the critical angle, then you're going to get that less, and then you are also going to have is a total internal reflection whenever you reach that point. All right, so question number 42. A parallel beam of light falls onto a converging lens. Which diagram shows what happens to the beam of light? And again, this is a converging lens, and by virtue of the word converging, it means then the rays must come together. But it is a lens, and so therefore it will go through and not reflected as shown in C. So the rays must converge, which comes together. That's what the word converging lens mean. It will not be reflected as shown in C because C is actually representing a what? Mirror. So D here has to be our correct answer. The rays will converge, meet at one point. Question number 43. Which two optical devices produce enlarged upright virtual images when the object is placed closer than one focal length from the lens or mirror? And again, we have done a number of examples, and I'll show you to draw the diagrams using concave lens. And one of the point that I mentioned is that in concave lens, the closer you are, concave mirror, I should say, the closer you are to concave mirrors, is the larger the object will become magnified, and it will also be virtual, which is behind the mirror, and again it will also be upright. All right, and so a concave mirror must be in our answer. So for sure now we know that A and B are out. And if we look at a lens in terms of lens now, for convex lens, we know that again the image will be enlarged, again it will be upright and be virtual. So yes, 43 will be our correct. 43D will be a correct answer. Now, for question number 44, is a specific electromagnetic wave has a frequency greater than microwave. The wavelength of this wave is longer than visible light. What is the name of this electromagnetic wave? And so again, to remind you, we just talk about that again. Remember how we did it? We said that radio, let me just write it down again. Radio, my information verbally, unless X news is gibberish. All right, so remember that. All right. And so if we have this again coming from radio waves or the gamma wave, then what happened to wavelength will what? Decrease. And so here they ask us here for the wavelength of this is longer than visible light. So if it's going to be longer than visible light, they want to know for sure it is infrared, microwave, and radio wave. Those are larger than visible light. So we have three options here, either R, M, or I. Okay? But there's something else they ask us here at the front part. They say the specific electromagnetic waves has a frequency greater than microwave. So if it is greater than microwave, just to mention here, all right, just to mention here, just to kind of put them in, so we're going to get it kind of easier. Going this way, the wavelength will decrease. Okay, the wavelength decrease that way, but going that way also, the frequency will, here the frequency decrease, the wavelength decrease going that way, but the frequency increases. And so if you look on the question now, it stated that this specific thing here has a frequency greater than microwave. So that means high is greater than microwave in terms of frequency, right? Matter of fact, infrared, visible light, ultraviolet, X-ray, gamma ray, they're all greater in terms of frequency than microwave. But it said now that the wavelength is longer than visible light. And so again, infrared is the one that we have two stroke on the, so it's fall between these two. Okay, so between microwave and visible light, we have our infrared. So infrared is the answer. So again, an easy way to remember this, remember radio, my information, verbally, unless X news is gibberish. All right. And so question number 45, we say diagram now shows the dispersion of white light by a glass prism. Here it said now, why does the dispersion occurs when white light enters the glass? So as white light enters the glass, there are a number of things you need to remember right here, is that the frequency of the waves must be the same. You need to remember that the frequency of the waves must be the same because they're coming from the same source. All right. However, now what you need to also know is that the slower the light is, the more bending will take place. If it moves slower, it bends more. All right. And also have a shorter wavelength as well. So what I'm going to make a note right here is that the ultraviolet light, it actually will be slower. Okay. It will be slower compared to red, because slower means you have a slower means that you have more bending. So this is slower because it bends more, we know for sure, compared to red. So notice red is not bending as much compared to how violet light is bending. So it's slower. And it also, because it's slower, also have a shorter wavelength. So it's slower with shorter wavelength. All right, so slower, and they put shorter wavelength there as well. Shorter wavelength. That's something we just need to know right there. And so let's go to the answers now and see which one is the best answer right here. So why does the dispersion occurs when white light enters the glass prism? And so for A, it said that here, the frequency of the red light decrease. So once the frequency changes, don't even look at it, it's going to be wrong. All right, the frequency in A and B, they're talking about frequency changes. Those are incorrect. So for C now, it said the speed of red light decrease more than that of violet. No, it's not true. The violet one is slower. So D said the speed of violet light decrease more than the light of red. And that is actually true because, again, slower light, they will bend more, and because they have shorter wavelength. All right, so they have shorter wavelength, so they bend more and move slower. Now, 46. It's a man stranded on an island, shouts for help, but is only able to hear in reply the echo of his shout from a cliff 858 meters away. All right, so poor man on the island, he better eat some coconut and drink some coconut, eat some fish maybe, and just chill. It's a nice life away from people. Sometimes it's good, but you know, it may be there for too long. All right, so here now, let's talk about this real quick. So this is speed right here, which is 330 meters per second, right? That is speed. And we also have the distance. So what you need to know now is not just the distance to find the time. We need to know about echo. Echo is a reflection of the sound wave. So it's a reflection of the sound wave. So if he talks here, it goes here, which is 858. You're going to come back to him, another 858. So the sound travel twice this distance. So you can just say 858 multiplied by 2, or just say 858 plus 858. So whichever one you want to do is not a problem, right? So the distance here that actually traveled by the sound, the distance traveled by the sound is actually equal to 858 multiplied by 2, or just 858 plus 2, whichever one you want to do is the same thing. You get 1,716 16 meters, right? That is in meters, cool. And so what we're going to do is to find time. Based on the formula, that time is going to equal to distance over velocity. So time is equal to distance over velocity. And so it's equal to now distance, which is 1716, divided by the velocity, which is 330. And so this is equal to 5.2. 5.2, yeah, that's 5.2 seconds. All right, so 5.2 seconds is our correct answer. So therefore, option C is the correct answer. All right, so let's go to the next question now. We're almost there for real this time. And so we're at 47, which is very close in sight. It's a large conducting sphere, A, is charged with charge while in contact with the positive terminal of a high voltage power supply. A light initial uncharged conducting sphere, B, hangs from an insulating thread as shown. And so there's something very important here, high voltage. So there's a high voltage power supply that is connected to it. That's very important right there. And so it asks us now what change accumulates on the sphere, and how does the sphere, and how does sphere B actually move as a result. And so again, because of the high voltage, just to make a note right now, something that you need to note as well, because of high voltage, the overall charge in the sphere will be 0. So when there's a high voltage connected to a sphere, the total charge inside of the sphere is actually 0. All right, and so therefore, if the charge inside of a sphere is 0 because of the high voltage, then it's going to remain neutral. And if it's neutral, and B is also neutral as well, because that's stated in the question that sphere B is also uncharged. So sphere B is uncharged, and so if A is uncharged because of high voltage, the total charge in it will be 0, and this is also uncharged, then none of them will move to each other. So therefore, is a neutral charge, no movement. So B will be our correct answer. All right. So for the small ball to move, then the sphere would have to be charged. And so if you just use a single positive charge beside this, then this will lose all its electrons and become positive charge, and therefore the B will move towards it. But in this case, high voltage connect directly to it, then the overall charge will be 0 or neutral, hence no movement towards the sphere. All right, for question number 48 now. It's a diagram shows three identical lamps arranged in a circuit. And so the lamps, they are identical. And so it said the current in ammeter A1 and A4 is 6 amperes. So A1 and A4 is 6 amperes as shown right here. So we have 6 amperes here, 6 amperes here. That means the total current in the entire circuit is 6 amperes, right? And so what we're going to talk about here now is that here is what is the current? It's what current is registered on ammeter 2 and ammeter 3. So ammeter 2 and ammeter 3 want to know what is the current. But we know the overall current based on ammeter 1 and 4 is 6. All right, so if 6 is there, and this is a parallel circuit, so we know that the current will have to be shared between them, right? It's a parallel circuit, so the current will have to be shared. The voltage will be the same. In a parallel circuit, the voltage is the same, but the current is shared. But let's now think about how the current is shared between this. It was shared in a certain ratio, yes? So the first thing to note right here now is that when current is in a series, because these two lamps here, this lamp I'm highlighting and this lamp here, they're in series with each other within that section of the parallel circuit, right? And so again, the current in the current within the series part will be the same. So first and foremost, how is the current sharing here is in a 2-to-1 ratio, okay? So there's a 2-to-1 ratio in terms of sharing the current. So I must kind of write it down. So easy way to look at it in this way. The ratio going to share in a 2-to-1 ratio. So 1 is for A1 and 2 is for A3. So the readings on these two must be the same, but the current will be shared among these two. So therefore now, if the ratio is shared in a 2-to-3 ratio, then the total of this ratio is 3. The little mathematics here, right? The total of this ratio is 2 plus 1 is 3. Now, what you need to know now that the current that we're sharing is 6 amperes. So we're sharing 6 amperes. We're going to divide this by 3. So we're going to get 2 amperes there. We're going to get 2 amperes to share between the 2-to-3 ratio. So when we say now, we're going to say 2 multiplied by 2 is 4, right? So 2 multiplied by 2 is 4 for the 2 right here. And then 1 multiplied by 2 is 2. So it's going to be a 4 amperes. Let's put our amperes here. It's going to be 4 amperes to 2 amperes. All right, so it's going to be 4 to 2. So A2 is the one that's going to get 4, and then this is going to divide by themselves again. So therefore, these will get the 2. So 4 go here, and then the 2 amperes will go at the bottom right there. All right, so just to quickly put that. So in the option right here, option C is the correct answer here. Is a 4 to 2. Okay, 4 to 2 current ampere. So again, this here will get the most current because only one, and these get the least amount of current because there are 2 of them sharing that same current there. All right. Next question here now, question number 49, and we're almost there. One more question to go after this. It said domestic solar panel has a power output of 350 watt. The solar panel receives an average of 5 hours of direct sunlight per day, right? So we receive 5 hours of direct sunlight per day, and the power output here is 350 watt. I must highlight that. So you have 350 watts, and our time is 5 hours. All right, so let's quickly see what you're going to ask for us right here to do. It said, what is the voltage? No, what is the average electric energy produced by the solar panel daily, and the cost of this energy if a kilowatt hour costs 20 cents. So if it's 20 cents per kilowatt hour, let's see how much we're going to get here. So we want to find the average daily electric energy produced in kilowatt hours, and we want to find the cost of the electricity. So let's now go and calculate those quickly. So let's find the energy first. So first and foremost, we need to convert this into kilowatt, because remember we're working with kilowatts, right? And even the question and the answer state kilowatt here. So kilowatt, so we divide this by 1,000. So you should get, if we divide it by 1,000, you're going to get 0. There's going to be 0.35 kilowatt of energy. And so that's kilowatt there. And the time here is 5 hours. So what we're going to do now is to multiply the power by time. We're going to multiply power by time to get our kilowatt. All right. And so what we're going to do is to multiply 0.35 kilowatt by the hours, and it's going to multiply this by 5 hours. And so if we multiply this by 5 hours, what we will get here is 1.75, yeah? 1.75, 1.75, and this is kilowatt, as we mentioned, kilowatt hours. All right, so if 1 kilowatt hours now was I think it was 20 cents. Let's go back for it quickly. Yes, it's 20 cents. So 1 kilowatt hour is equal to 20 cents. And so what we're going to do now is to find 20 cents, and 20 cents is actually $0.2, right? So what we're going to do is to multiply 1.75, multiply this by 0.2, which is 20 cents divided by 100 is 0.2 in terms of dollars. And so what we're going to get here is 0.35, $0.35, right? All right, so get that amount of money we're going to spend right there in terms of dollars. So actually 36 cents. 36 cents. I'll get back some zoom into this. All right, so 36 cents or $0.36. And so that's actually 35, you know. It's 35, not 36. My mistake. 35, yeah. So it's 0.35 and not 36, right? Yeah. All right, so 0.35 or 35 cents. All right, so now quickly, now let's see what our answer here. Remember, it's 1.75 and 35. So yeah, so this here is the answer. A is our option right here. That's the energy, and that is the cost. All right, let's look at number 50. And number 50 is after some building work in a house. Let's get back down to the whole question first. It's the last question here, right? Is after some building work in a house, bare uninsulated live wire is left protruding from a wall. So is uninsulated, protruding from a wall. So what is the greatest hazard? And so if the wire is there, all right, and is hanging, is uninsulated, that means just the wire by itself, the bare wire, all right? That means it's a fire. A fire can be caused definitely if it connected to another wire or it touches the other wire, which is the ground, then yes, you may have a problem. You see, a fuse may blow. If a fuse is blow, that's a great thing. But the wire is just protruding. That means it's not capable of touching anything that easily. But if you walk and touch that, then yeah, you may get electrocuted. So electrical shock is the greatest possibility right there. All right. So folks, again, this is the end of another review here. So again, be safe, take care, do well on the examination. Talk to you soon. All right.